Okay, this chapter dealt with converting any time domain signal to frequency domain. Okay, any time domain signal and to see the characteristic of that signal in frequency domain. Okay, this is a very interesting topic which will let us know about how the continuous time signal and how the discrete time signal behaves in frequency domain. Okay, so now here if I talk about a signal, then we have four different types. Continuous time, periodic signal. Second one is continuous time, non-periodic signal. Third one is discrete time, periodic signal. Fourth one is discrete time, non-periodic. Okay, so depending on the type of signal, there will be a different type of frequency domain analysis. Okay, so there are basically the four different types of frequency analysis depending on these four type of signals. Okay, I should say for the first category, for continuous time, periodic signal, we have called Fourier series. Which is called CTFS. C for continuous time Fourier series. Time domain, frequency domain. These two are related in this way. Second one, for continuous time non-periodic signal, we have Fourier transform, which is CTFT, continuous time Fourier transform. Okay, this first two letters for the time domain, second for the frequency domain. For discrete time periodic signal, we have again Fourier series, but this time it will be called DTFS. Okay, discrete time Fourier series. So fourth, we have seen that whenever signal is periodic, it is becoming a Fourier series. Whenever the signal is non-periodic, it is Fourier transform. The fourth category which is remain is for discrete time non-periodic. We have again Fourier transform. This is called DTFT. Remember, DTFT is different from DFT. Okay, we will see the DFT when we will go to that topic, but presently you just know there are four different types: CTFS, continuous time Fourier series; CTFT, continuous time Fourier transform; DTFS, discrete time Fourier transform; and DTFT, the first discrete time Fourier series, and the last is discrete time Fourier transform. Okay, so these are the four different types in which the frequency analysis of these four different types of signals can be done. And important thing is, any signal in nature can be put out of any of these types. Okay. Now coming to the first one. Fourier series for continuous time periodic signal. Now for this thing, when I say continuous time periodic signal, I can draw a signal, a sinusoidal wave, of any phase but of period omega. Omega naught is the frequency for this. So I can write xt equal to sine omega naught t. Okay. In exponential form, I can write it as something like this: 1 upon 2j e to the power plus j omega naught t minus e to the power minus j omega naught t. Okay. Now, this is xt can be represented from the above relation. We can find xt can be represented as a sum of the exponentials I can write here coefficient ck e to the power j 2 pi k f naught t, where omega naught equal to 2 pi k f naught t equal to k tending to minus infinity to plus infinity. For the above case, the k value will be minus 1 and plus 1, and k equal to 0 will not be there. Okay, so if I rate k equal to minus 1 and plus 1 and substitute in the above equation, I will get something like c of minus 1 e to the power minus j 2 pi f naught t plus c of plus 1 e to the power plus j 2 pi again f naught t. Okay, so if we match this with this expression, we can find certain similarities. I can write c of minus 1 equals to minus 1 by 2j, c of plus 1 is equal to 1 by 2j. Okay, so from this I got the idea that any periodic signal can be expressed as a sum of exponentials, weighted exponentials, and can be related by this equation. This is a very general equation for writing any Fourier series. K equal to minus infinity to infinity ek e to the power j 2 pi k f naught t. This equation is called synthesis equation. Okay, synthesis. Why synthesis equation? From knowing ck, I can synthesize xt. Okay, that's why it's called synthesis equation. Now, how to find the ck? Okay, to find ck, there is another equation which is called analysis equation. Analysis equation, it can be written as ck equal to 1 by tp. Okay, now this is a continuous time. I can write here integrate for one time period xt dot e to the power minus j 2 pi k f naught t dt. Okay, this expression here is called kernel. This is actually helps in finding the CK. Okay, this equation is called analysis equation. Why analysis? From xt I am getting CK. CK are nothing but the coefficients of the weighted values for which if we multiply with exponential and add, we will get the xt. Analysis equation. Equation is very helpful and to be remembered. Okay. So now we have seen signal is continuous time. Signal is continuous time xt, but their coefficients are discrete. So for continuous type periodic signal, Fourier series is discrete and non-periodic. This has to be remembered. Okay. Important note, you can write it as a note. For continuous time periodic signal, Fourier series is discrete and non-periodic. Okay. Now the relationship, what kind of CK is? CK is generally, again you can write down as a note. Note 1. CK are complex valued. So once they are complex valued, that means the complex conjugate also occurs. Okay. That means CK and C of minus K are complex conjugate. Okay. That means magnitude of CK is equal to magnitude of C of minus K. But phase are different. Phases of CK is equal to minus time of phase of C of minus. That means this is even symmetry, this is odd symmetry. Okay. Now I can write this exponential Fourier series in terms of trigonometric Fourier series also. Okay. So if I convert this exponential Fourier series into trigonometric Fourier series, the formula will be, you can write again note, just write to remember, exponential to trigonometric. I can write xt is equal to a naught plus summation k equal to 1 to infinity ak cos 2 pi k f naught t minus bk sin 2 pi k f naught t. Okay. This becomes, if we compare with the exponential Fourier series, a naught is equal to c naught, and this is a DC value. Okay. AK is equals to 2 mod Ck cos theta k. Bk is equal to 2 mod Ck sin theta k. Okay. So if Ck is given, we can find AK and Bk by this relationship. Okay. Now just see the power density spectrum of for this periodic signal. Periodic signal has infinite energy. Infinite energy because they extend from plus infinity to minus infinity, but they have finite average power. Infinite energy, but finite average power. Signal has infinite energy. Infinite energy because they extend from plus infinity to minus infinity, but they have finite average power. Infinite energy, but finite average power. Okay. I can write power is nothing but 1 by Tp integral of xt whole square. This integration limit is over 1 period dt. Okay. In terms of its Fourier coefficients, I can write summation k tending to minus infinity to infinity ek whole square. Okay. This, that means, let this be 1, let this be 2, 1 and 2 are equal. This is called Parseval's relation. Okay. Now, note power density spectrum is a even function. Okay. In terms of trigonometric Fourier series coefficient, I can write Px is equal to a naught square plus 1 by 2 summation k tending to 1 to infinity ak square plus bk square. Okay. This is one more important relation which we can find. If we plot this power density spectrum, the spacing between these lines, let this be 0, this is f naught, this is 2 f naught, this is 3 f naught, 4 f naught, dash dash dash. Minus f naught, minus 2 f naught, minus 3 f naught, minus 4 f naught. The spacing between this line is equal to the one fundamental period. Okay. Or this is equal to the fundamental frequency. Reciprocal of this is equal to the fundamental period. Write down. Magnitude here is mod ck square. Spacing between line is equal to 1 fundamental frequency. Okay. Now let us determine the Fourier series and power density spectrum for rectangular pulse train signal. A very important, help us to analyze many things. series and power density spectrum. Okay. For rectangular pulse train. I can draw XTS something like this. It has got the pulse width as tau and period as TP. Minus TP. Okay. Let the amplitude of this be A. So, by using a synthesis analysis formula for this, I know Ck can be written as 1 by Tp integral for whole period xt dot e to the power minus j 2 pi k f naught t dt. Okay. So for this, if I take one period, I can write 1 by Tp integral for minus tau by 2 to tau by 2, because between minus tau by 2 to tau by 2 the amplitude is A. Otherwise at other point it is 0. Okay. A dot e to the power minus j 2 pi k f naught t dt. Solving this integral, I will get A by Tp e to the power minus j 2 pi k f naught t upon minus j 2 pi k f naught within the limit minus tau by 2 to tau by 2. Solving this, I will get A tau by Tp sine of pi k f naught tau upon pi k f naught tau. This function has got a special feature, a special name also, and it is called as sinc function. Okay. This is equal to Ck. Now from this C0 will be A tau by Tp, because limit k tending to 0 sine theta k upon theta k is equal to 1. Okay, that's why I can directly write A tau by Tp. This C0 is nothing but the DC value. So the DC value for the given pulse train is nothing but A tau by Tp. Now coming to the other things. If I plot Ck, then plot will be something like this. I'll draw one sync wave. This is not the actual one. If I plot Ck in this, that means I have to plot the straight line like this, and they all are discrete place at some point which is equal to the harmonics of the frequency present over there. Similarly on this side also. That means whenever I will give a periodic signal in any spectrum analyzer, I will see something like this. Components spikes place at different frequency interval. Those frequency interval are nothing but equal to the harmonics of the fundamental frequencies. Okay. Now, note first spacing between lines is equal to fundamental frequency. Okay. I should say the spacing between the consecutive lines. Okay, so spacing between the two lines is equal to twice of the fundamental period. Spacing between three lines is equal to 3 times the fundamental period. Now, let this be first note. Second note. We have seen Ck is equal to A tau by Tp sine of pi k f naught tau upon pi k f naught tau. If we keep Tp as fixed and change tau, then the effect of decreasing tau is to spread the signal power over the frequency range. Okay, that means if tau decreases, then frequency spread will increase. Line spacing will not change. Okay. Same thing, reverse thing will happen when tau increases. If tau increases, frequency spread will decrease, but line spacing will remain same. Now, one more effect with decreasing tau is, if tau decreases, then magnitude also decreases. Magnitude decreases, but it is spread in the full frequency range. Okay. The reverse thing will happen when the tau increases. Third point. Again, if we take the same case, if we keep the tau fixed and we change the Tp, that means the period, then what will be the effect? Now in this case, if Tp increases means what will happen? First effect is A tau by Tp will decrease. Okay. Another thing is Tp increases, f naught decreases, thus spacing between lines will reduce. Okay, reverse thing will happen if TP decreases. If TP decreases, f naught will increase, and the distance between the lines will also increase. On the basis of this, we will solve few problems which have appeared in GATE exams. First one, find Fourier series coefficient for xt shown below. Xt is shown like this. I have impulses present at various time intervals. This is a periodic. Amplitude is 4. Okay. Find the Fourier series coefficient for this. Solution. Period here is period t is equal to 2. Now Ck we know 1 by Tp integral for full Tp xt e to the power minus j 2 pi k f naught t dt. So I can write 1 by 2 integral from minus 1 to 1 xt is nothing but 4 times of delta t e to the power minus j 2 pi k f naught t dt. This is equal to 4 by 2, which is equal to 2. Thus Ck will have same value at each point. So if we look for the plot of this, everywhere it will be 2. Okay, this is frequency domain, this is the for the given Fourier series coefficient, for the given Fourier series, or we can say find the time domain signal. Ek can be written as j times of delta of k minus 1 minus k times of delta of k plus 1 plus delta of k plus 3 delta of k minus 3. The fundamental frequency omega naught is 2 pi. Okay. For this we have to find the time domain signal. Now it is just a reverse process. Okay. Looking at the solution of this, we have to find xt, use synthesis equation k tending to minus infinity to infinity Ck e to the power j 2 pi k f naught t. Okay. So comparing with this thing, I can write j e to the power j 2 pi t minus j e to the power minus j 2 pi t plus e to the power j 2 pi into 3t plus e to the power minus j 2 pi into 3t. These two terms will give you sine component and these two terms will give you the cos component. So this will become j 1 by 2 j 1 by 2. I have to write j here. This will become j here. Let firstly 2 into j into 1 by 2j e to the power j 2 pi t minus e to the power minus j 2 pi t plus 1 by 2 e to the power j 6 pi t plus e to the power minus j 6 pi t. So this will become minus 2 sine 2 pi t plus here I also have to multiply it by 2 cos 6 pi t. So this is a time domain signal for the given question. We have to follow the synthesis equation and analysis equation always for getting the results. Okay. One more problem. If xt is a periodic signal with period t and Fourier series coefficient as xk, then determine Fourier series coefficient for yt, where yt is equal to x of t minus t naught plus x of t plus t naught. Solution. How to determine this? Okay. Just see, I can write here x1k having a Fourier transform for x of t minus t. This is equal to 1 by tp. This is a time shift. Time shift will not change the period. Okay. Tp x of t minus t naught e to the power minus j 2 pi k f naught t dt. Substitute t minus t naught equal to tau. Will implies dt equal to d tau. Limit will remain same. Then x1k is equal to 1 by tp integral for full tp x of tau e to the power minus j 2 pi k f naught tau plus t naught dt. Okay. This will change x1k is equal to e to the power minus j 2 pi k f naught t naught 1 by tp integral tp x tau e to the power minus j 2 pi k f naught tau d tau. This is equal to e to the power minus j 2 pi k f naught t naught x. This is same as this. Okay. Similarly, x2k will become e to the power plus j 2 pi k f naught t naught xk. Now, x of t minus t naught plus x of t plus t naught is equal to x1k plus x2k. Okay, this will become e to the power minus j 2 pi k f naught t naught plus e to the power plus j 2 pi k f naught t naught outside xk. This is equal to 2 times of cos 2 pi k f naught t naught xk. So this is a relationship for or we can say this is a Fourier series for yt, where yt is equal to x of t minus t naught plus x of t plus t naught. Okay.